First, recall that a theory is complete if for every sentence we have either that T proves sigma or it proves not sigma. This definition is a little bit different from the original one, right? Where we also required that the theory is actually consistent. But subsequently, we saw that inconsistent theory actually proves every formula. So if we have this either or here, right, this exclusive or, that automatically rules out inconsistency. And as I already mentioned in the introduction, when we started looking at term models, we noticed that in order to show that the canonical term structure is a model of T, we needed T to be complete. And that was in particular for the case when we wanted to carry the induction from psi to not psi. So the question is now, can we extend T to a complete theory T star? If this is indeed possible, well, then every model of T star, since T is a subset of T star, right? Every model of T star would also be a model of T, because if a structure satisfies every sentence in T star, it also satisfies every sentence in T. It is often helpful to look at complete theories through a little bit of a different concept, namely that of maximal consistency. So a theory is maximally consistent if it is consistent and it has no proper consistent extension. And the connection with completeness is pretty straightforward, namely any maximally consistent theory is complete. And if T is a complete theory, then the deductive closure of T, given by this, so looking at all the sentences that T can prove, is maximally consistent. Now you should definitely try to prove this yourself. There's essentially one fact you will need for this, and that's the following, namely that T proves the sentence sigma if and only if it's the set, if I add the negation of sigma to T, is inconsistent. And likewise, so T does not prove sigma, right? So it does not prove sigma if adding not sigma to T is consistent. And the main tool to prove this is the deduction theorem. So we now come to the completion of theories, or the possibility to complete theories. This is known as Lindenbaum's theorem. We state it here for countable languages, which was the case that Lindenbaum dealt with. So let T be a consistent L theory, where L is a countable language. There exists an L theory T star extending T, such that T star is maximally consistent. Since L is countable, in order to prove this, right, since L is countable, we can enumerate all L sentences as S sub n ranges over the natural numbers. Right? If L is countable, there are indeed only countably many L sentences. And then we do a recursive construction. We start with T, and then and in each step, we throw in for the sentence sigma n or the negation, depending on what Tn can prove. So if Tn proves sigma n, so in particular if sigma n is already in Tn, we just throw it in. If it does not prove sigma n, we throw in the negation. And then in the final step, we'll just throw everything into one big set T star. It is not too hard to verify that each Tn is consistent. For that, as before, the crucial part is that theory T proves sentence sigma if and only if adjoining that the negation of sigma to t makes that theory inconsistent. So using that, you can show that by induction that each Tn is consistent. And then that T star is maximally consistent. There, maximality is not hard to see, and that it's consistent again follows that if you are inconsistent, it actually shows in already a finite subset of T star. So if T star were inconsistent, there would be a finite subset of T star that would have an inconsistency. So once you've done that, you can think about how to extend Lindenbaum's theorem to the case of arbitrary languages. And as you may already guess, you would use the well-ordering principle or Zorn's lemma to do that.